All right, as we continue on in our forces in motion unit, it is now time to talk about probably someone we need to give a lot of credit for in regards to forces in motion. That's Isaac Newton. Although he did get many of his ideas from scientists that came before him, he definitely verified many theories and came up with some things on his own that really changed the way that we look at how the world operates. So we have Newton's first law, and this one should seem very familiar. Sometimes it's even called the law of inertia. And we had a vocabulary word last week of inertia. And it's important for us to understand that inertia is that tendency of an object to either stay still or to stay in motion, depending on when a force acts on it. So let's take a little bit closer look at that. They're going to continue to skip that. Whoa, holy cow. I don't know where other slides went on that, so let me go back. Apologize on that one. Must be on the wrong slideshow. We talked about this last week when we talked about inertia, and we can go back to our example of a rock. We are not surprised when we come outside and a big giant rock is still sitting there. That rock is not going to move on its own. It is happy to sit there, and that is part of inertia. An object at rest tends to stay at rest. But there's a second portion to that, unless a force acts on it. So that rock is sitting there. If you pick that rock up, if you throw the rock, if you roll the rock, you have now put a force on or into the rock, which causes it to change its position or have motion. And that's something that's very important to understand. The part that gets a little more complicated is once the rock is in motion, it would typically stay in motion and never stop unless a force acts on it. Now, we know that nothing continues to move. No matter how hard you throw the rock or a ball or anything else, it doesn't continue to go. It eventually, number one, if you throw it up in the air, it comes back down to the ground, and then number two, might roll for a bit, and then it's going to stop. So we have a couple of forces there that are acting against the motion of that, friction being the biggest one of them all, because it's a force that acts against moving objects. Now it looks like we're moving to law number 2. Newton's second law. And we touched on this last week. The greater the mass of an object, the more force you need to move it. Now, none of us are shocked about this. This goes back to when we talked about the toy train versus the big train. The bigger something is, the more force you need to move it. That's not a shock. No one in here would be shocked that it's easier to move a toy train than it would be to move a giant train. It takes more force. With that being said, it also takes more force to stop a big moving object. It also takes more force to stop a big moving object. That is why you do not want to pull out in front of those giant trucks that are hauling things up and down the highway when you're driving, because if they have to slam on their brakes and you slam on your brakes, you are in a small car. They're in a big giant truck. You will stop much faster than them because they are trying to stop much more mass, and they will end up smashing into the back of you. And it's very dangerous, obviously, to do that. So you have to be very careful when those things are happening. But this one we talked about. The bigger something is, the more force needed to move it. We go back to our example of if we had a beach ball and a bowling ball sitting on the baseball field. We all know that it would take less force to kick that beach ball, and none of us are stupid enough to kick the bowling ball because we don't have enough force in our legs to move a bowling ball. It would break our foot or break our leg or something, and that would be a pretty bad day. So honestly and truthfully, Newton's second law isn't anything really new to us. We just now have a word for it. Last week we just talked about how it's easier or harder to move things with more mass. Now we know that that's Newton's second law. The greater the mass of an object, the more force you need to move it. There's some good videos on here, some guys trying to move that big boulder that we've talked about in class, and you notice that there's 3 people here chugging on this boulder. I would recommend watching that. Here's another video, pretty fun video. I have no idea how we came across this video of someone throwing a small stone and skipping it across the water. Again, you've got 3 guys trying to move a giant stone because the more mass something has, the more force it takes to move it. And you have this guy skipping a stone. So it's pretty easy to notice and think about those two. Newton's third law might be a little more different. That's something we're probably going to have to dig into a little bit more. But it's for every action, there is an equal and opposite reaction. With that being said, if 2 of us were standing in front of each other and let's just say a person pushed someone else that's in front of them, the person that they pushed would move backwards equal to the amount of force that was pushed into them. Because you wouldn't expect them to go flying back, 3,000 feet unless it's Superman pushing you, right? And you also wouldn't expect the person to not move at all if someone pushed them, because obviously if that happened, they didn't push with any force at all. If you bounce a ball, so let's just pretend you have a bouncy ball. We know that if we bounce a ball just lightly enough, it'll bounce right back up into our hands. And we can do that over and over because we're putting just enough force into the ball when we hit it off the floor. The opposite reaction is the ball comes back up almost to the same height. Now, if you take that same bouncy ball and you throw it at the ground as hard as you can, you know that the ball is going to bounce way over your head because you have now put more force into the ball. And when the ball hits the ground, it's going to react with equal and opposite force, and it's going to come back up off the ground and bounce much, much higher into the sky. There's some videos in here that I would recommend watching that would go along with that. You won't have to do the collaborative board. Here's some examples of Newton's third law. If you ever shoot a gun, there will be something that it's called, it kicks back on you. And the reaction is that backwards force of the gun, the recoil, hits back into your shoulder. And that's why you have to hold a gun a specific way, because it's obviously a lot of force coming out the front, but it can't just do that. The equal and opposite reaction is if there's something being pushed out the front, it's going to move the gun backwards. Launching a rocket is probably the best. You're pushing down on the earth with great force, which is going to push the rocket upwards and away from the earth. If you jump into a boat, or if you were to jump onto like a pool float or something in the pool, when you jump in, because you're jumping up, that downwards force is going to push the boat or the float down into the water, and that boat or float is going to push you back up a little bit as well, causing you not to go down as far in the water as you normally would. If you're hitting a nail, you're swinging a hammer down, driving the nail into the wood, but there's going to be some force that comes back up. If you don't hold a hammer tightly and you swing and hit something, it will bounce back up and hit you in the face if you're not careful. That's why you should always wear safety glasses when you're working on things at home, because you just never know when you might swing a certain way. Sitting in a boat and you push on another boat, if that were to ever happen, if you're both be in a boat, that's kind of similar to if you're both on roller skates and you're facing each other and you both push. Both of the boats would move back away from each other, or if there were 2 people in roller skates and they pushed each other, both people would roll backwards and away from each other. So there's some more examples of Newton's third law. And this is something for kids in class. So it's a very, very quick overview of Newton's 3 laws. Obviously, we'll be going over those all week, getting ready for our test that we need to have here soon. Probably not this week since it's a benchmark week. But we'll start to prepare for it, and we'll get ready for it probably early next week. We'll start reviewing. Maybe we'll have the test on like Tuesday or something. We'll see what it looks like in class, making sure people are understanding things in this as the week ends. If you have any questions, send me an email, and I will chat with you soon. Don't forget to smash that like button and subscribe.